I'm pretty stoked this is the last video, huh? Well, maybe some of y'all are like, hey, I'm enjoying this. I have to take physics. This is the crap we do in physics. Of course, everything looks a little bit different because they use different pictures or variables. They also skip past a lot of the nonsense that us math people do. But a lot of times when you're sitting in a physics class and your physics teacher just flies through stuff and goes, well, because it is. It's because you're supposed to have already taken a math class to have learned these things. So they skip past. So this is highly valuable for trying to understand a lot of these tough physics concepts. Where if we can understand a little bit of the math at the beginning, it's going to make it a lot easier for you to hear your professors tell you all about the physics that you're going to need for your major. Or maybe you just have to play the game and take a physics class like I had to take a physics class just because, well, oops. It was on my little thingy saying you have to take it. Either way, we better know some crap. That's me. Let's get it. Let's get it. So here's our procedure. This is the game. So we're talking about solving force on dam problems. So we're going to think about like dams, or you can think about it anyway. It could be just some sort of plate in a pool. There's a lot of different ways we can do this. Now, number one, please follow the parenthesis. So we're going to draw a y-axis on the face of the dam in the vertical direction and choose a convenient origin. This is often taken to be the base of the dam. Make it the base of the dang dam. The dam. And then we're going to need to, here's the hard part. This is the tough part. We need to find the width function, w of y, not x. But we think of widths typically as x's. So we're going to have to do a little work like we've done in previous problems. That's going to be the tough one. And then it says, if the base of the dam is at y equals 0, please make it y equals 0. You can set the base anywhere you want to, but I'm begging you to put it at y equals 0 to make life easier. And the top of the dam is at y equals a. Then the total force on the dam is what is sitting there. Our pressure times our gravity times the depth times the width, integrated from 0 to a, all with respect to y. Now here's a problem. Sorry that I'm using so many of your book problems. I don't know if any of you actually know you have a static ebook. You have an ebook that you can look at inside of my lab. So you could go through these and see them yourselves. And I'm stealing all of these because they already have pictures. Also, I'm not super comfortable with all of this information. This doesn't come naturally to me because I'm a mathematician. I'm not a physicist. So if you ever want to check something with better pictures, go for it. Check these out. So here we be. Force on a dam. A large vertical dam in the shape of a symmetric trapezoid. It needs to be symmetric or we got problems. It has a height of 30 meters, a width of 20 meters at its base, and a width of 40 meters at the top. What is the total force on the face of the dam when the reservoir is full? Let's check it out. Well, first, this thing that I kept crying about, saying, hey, let's create an x and a y axis that start at the base of this thing. Let's put it at the bottom. Let's make a y axis. I'm going to try and split those. It might not be symmetric, but use your imagination. And now we have an xy graph where the base is at the bottom and the top is at the top. All split up nicely. All right. Okay, so let me write the formula over on the side. So we're going to say the formula is equal to the integral of rho times g. But the pressure of water, the density of water is 1,000 kilograms per cubic meter. Gravity is 9.8 meters per second squared. So I'm going to write this as 9,800 from 0 up to wherever we're going. And then we're going to need our A value minus our Y value. Oh yeah, that's going to be A. We'll replace that in a second. And then we're going to have to find the width all in terms of Y. The tough part of this problem is right here. Well, understanding what the question is asking, memorizing your formula. And then we have to get into how do we solve for that width, but in terms of Y, not in terms of X. Because if you take any width, some width, this is actually equal to x and x, or 2x. We don't want it in terms of x's, we want it in terms of y. Well, now let's go to our bounds of integration. See that A? They match. The A is the height. The A is the height. So we're going from 0 up to 30 of 30 minus y. But now the fun begins. We have to we have to figure out how do we get those x values in terms of y. But before we start, the width is equal to 2 of those x's. You see how we split it in half? So x, any x value we choose, we're going to have to multiply that thing by 2. And as we had done before, I'm like, wait a second. If this is 20, if that's 20 meters, I think half of that, this point here, wouldn't that be 10? But the height's 0, so we get 10 comma 0. And then we look up top and we're like, well, this width here, that's 20, right? But since we set it up on an xy axis, we can say like, oh, well, that's 20. All right, I had to move over 20 units. Now what's y? It's 30. Do you see what we're going to do next? Do you remember from the past videos? Hey, look, there's some sort of line that connects these two. There's a line that connects these two dots. So first, we want to find the slope of the line, right? The slope of the line, and then we're going to plug it into y minus our y1. And then we're going to have our slope times x minus our x1. So we need our slope right here. And then we're going to choose 2 convenient points, either 20 comma 30 or 10 comma 0. 10 comma 0, 10 comma 0. So we're going to choose whatever it is you want. So let's go find our slope. So maybe I call this one x2, y2, this one x1, y1. So our slope is going to be 30 minus absolutely nothing over 20 minus 10, which is equal to 3. 3. And now we're going to choose a point, an x and a y value. We could choose 20 comma 30, but who the heck wants to deal with bigger numbers when you could deal with smaller numbers? So we're going to say our y1 is 0. We can say that our x1 is 10. Well, we're getting closer. We're going to be able to solve for x in terms of y. So we have that y is equal to 3 times x minus 10. So let's divide by 3. We get 1/3 of y is equal to x minus 10. Add over the 10 and we get, oh, there it is. Is that right? X is equal to 1/3 y all plus 10. But I'd like to do something really quick and see if you can't follow this. If you divide out 1/3 from this whole thing, I'm trying to make life easier. You don't have to do this step. But if you divide out 1/3, when you factor, it's like you're multiplying by its reciprocal, 3. Double check that I'm correct, because we're much better at distributing than we are at factoring, yeah? 1/3 of y would become 1/3 of y, and 1/3 of 30 would become 10. So we found our x value. Dope, so we just take this and plug it in, right? We just take this and we're like, just plug it in. Not so fast. The width is 2 times our x value. So before we're allowed to plug that in, before we're allowed to do anything with it, we got to multiply our x value, which is this, well, the width is 2 times our x value. 1/3 y plus 30. So we get 2/3 y plus 30. And that is our width function, all in terms of y. You see kind of why I took the 2/3 out? Because then it removes a lot of the work we need to do. So actually, I'm going to move this thing down now, and let's get to it. Start plugging in all the stuff we need. Well, of course, we got our 9800 evaluated from 0 to 30 of our 30 minus y. And then once we pop this thing, I'll use a different color. We have 2/3 times y plus 30. We need to make sure to write our dy. Got to be proper about everything. But we can yank that 2/3 out to the front. So 2 times 9800 is 19,600. We go 19,600 over 3, evaluated from 0 to 30. Oh, and by the way, if we're doing hydrostatic pressure in class, like on a test, here's your answer. I'm not going to ask you. I'm not going to ask you to to do those whole they're always going to be large ass numbers like this. But for a homework problem, we would need to do it. So we have 30 minus y times y plus 30. Oh, how freaking convenient. It's like this problem's cooked up or something. So I'm hoping you know what a difference of squares is, right? You could write 30 plus y. See the difference of squares now? So you have 0 to 30 of 900. That's 30 squared minus y squared dy. Now let's find our antiderivative. Let's go. 19,600 divided by 3 for 900y minus y cubed over 3, evaluated from 0 to 30. This is where you bust out the calculator. We have 19,600, and I think your homework might do this in a little bit of a different manner. It might give you the scientific notation of like 1.18 times 10 to the 8th or some crap like that. So let's see what it is. We get 900 times 30 minus 30 cubed divided by 3 minus absolutely freaking nothing. 19,600 over 3. And then what is 900 times 30? You could do that in your head though, can't you? You could do that in your head. You know, 9 times 3, right? And then maybe like add your frickin' zeros. Yeah. And then what's 30 cubed? I don't think anybody knows that. I think that's still a mystery. That's 27,000. Let's divide it by 3. And we get 9,000. So 27,000 minus 9,000. I think it's 18,000. So we get 19,600 over 3 times 18,000. Oh my goodness. These are some big ass numbers. So times 19,600 is equal to a big ass number. 3528 and then 5 zeros. Not a shocker. All over 3. If you divide that thing by 3, you get approximately 117600000. Oh my goodness, that's so many freaking zeros. So approximately 117,600,000 joules. But if you were to write this thing in a scientific notation, you call it approximately 1.8. Oh, I have my numbers off. 1.18, my bad. I can't read. I need to work on that, you know what I mean? I am a teacher. 1.18. So we're saying we're putting the decimal place there, so it's 1, 2, 3, 4, 5, 6, 7, and 8. So times 10 to the 8th joules. And that would be how you'd write it in scientific notation. And if you're curious, that dam is holding up about 26 million pounds, or about 13,000 tons. That's a lot. That's a lot of force on that dam. Oh my goodness, look at that one problem. There's your hydrostatic pressure. There's the end of physics. We're moving into chapter 8 now. Fortunately for your teacher, I'm super stoked because we're getting into the stuff that I'm actually pretty good at. Now that I say that, I'm going to make tons of errors, but I like the next section. It's all of our integration techniques. We've done our physics. We've done all the shapes. I think we're ready to go. Sweet. See you in the next.